Hi, everyone. Welcome to the second episode of Quant Club. I'm Michael Oliver. I'm the chief scientist at Numerai. Uh, Today, I just want to answer any questions people have about anything Numerai related and data science related, and also go over this paper. Why do tree-based models still outperform deep learning on tabular data? It's sort of related to a discussion we started to get into last week, and just an active area of research and something that is quite relevant to Numerai participants. Um, so let's start with anyone who's attending, if anyone has any questions or anything they want to say before we get started and going into the paper, I'd love to hear that. You can just raise your hands or otherwise ask questions. Anyone know? Okay. Um, cool. Have people here read this paper? Any sort of, if you've read the paper, let me know. If you haven't, that's fine too. If you could, yeah, just in the chat or whatnot, just let me know if you have actually read the paper, so I can sort of um, know what you guys know and don't know. Okay. So yeah, the reason I wanted to talk about this paper was because it's been known for a while that tree-based learners like random forests and gradient boosting machines typically do quite well on tabular data, and which is fine and great. But neural networks, there's been a lot of really good research on them over the last decade or so. That's seen them get state-of-the-art performance on many different types of tasks, but the sort of notable exception generally has been tabular data, at which these gradient boosted trees and random forests typically still excel. And people keep coming up with neural network architectures that they say are better or competitive with tree-based learners. Um, but it's, as it seems to be often the case, that they don't do a really good job of creating these baselines for the models they're comparing against, where they'll put a lot of time into hyperparameter optimizing their new fancy neural network-based model, where they're just use sort of very out of the box parameters for a gradient, for like XGBoost or something, and then say that they have a model that is better. The reason I like this paper is they try to be very fair to all the methods and do sort of equal hyperparameter searches for all the methods they look at. They look at a few different tree-based learners and a few sort of simple and also more recently proposed architectures for and neural networks that are sort of designed to handle tabular data, and do it across a couple of different data set sizes that are sort of normal tabular data sizes. I mean, they are using a lot of the experiments are on a medium-sized data set, which is 10,000 samples. Um, and they do show that sort of the gap does actually get a little bit smaller with larger data set sizes. And the question for Numerai participants is like sort of what is the data, like how does our data set compare in terms of number of samples? And there's a couple of different ways of actually looking at this. I mean, we do have a couple million rows, uh, which makes you think maybe it is actually a much larger data set than this, like a 10,000 sample. Um, but there's a particular interesting structure to our data that makes it a bit different. The eras um, are sort of the relevant unit of data in a lot of ways. And we only have a few hundred of those. Because you're trying to predict well in each era, um, it's the samples are not kind of really independent in sort of a standard way. And so it's not like you have 2 million different samples, and all that really matters is predicting any given sample correctly. What really matters is your performance per era. And so when you look at it that way, you might say that we only actually have a few hundred samples. And so maybe it's actually quite a small data set. Um, it's so I think some of these the papers like this are quite relevant. looking at the sort of medium and small data domain to Numerai in particular. So another thing I liked about this paper was that rather than just saying like, oh, this method works better than this method, they actually try to investigate what it is about the method that gives it a performance advantage. What are sort of the inductive biases of tree-based learners that seem to help them with tabular data? And they try a few different experiments and give some good intuitions about that. So let us dive in. So they're just sort of introducing the problem and setting it up. They are using sort of 45 different tabular data sets, and they're not particularly high dimensional. Ours is higher dimensional than most of these. And they're trying to basically clean it up and make them all sort of the same thing. But it's nice that they actually sort of release this and have the sort of this tabular benchmark that they have are releasing for people to use and compare in future papers. Hopefully people take advantage of that so that when they come up with new deep learning based methods that are for tabular data, they have a sort of better basis of comparison. But we'll see how that actually plays out going forward. Okay. So here are the set of models that they're benchmarking. They're benchmarking a classic multi-layer perceptron and just using a slightly fancier learning rate scheduler, but really just a very simple MLP. A ResNet is basically just a sort of upgraded neural network with some fancier things like batch normalization, and ResNet means it has skip connections between layers. That's basically just an identity. So a layer is basically just the output of a layer is its output plus its sort of input, or the input from a couple layers back. It's just a method that allows gradients to sort of flow better through a network and makes training neural networks a bit easier. They're using, and then two sort of transformer-based models that are specifically designed for tabular data. And they make these really nice plots, which are in terms of number of random search iterations. So they're basically, this is sort of, this axis is sort of how much hyperparameter optimization they're doing. And on the y-axis, they sort of have this normalized accuracy. And you can see that basically all the methods improve as you do more hyperparameter searching, which is not surprising. But what in both the classification and regression tasks, you see that basically XGBoost in green, the gradient boosting tree, which is basically the scikit-learn's gradient boosting library, tend to do the best in classification and regression tasks. And so this is using only numerical features, and this is using numerical and categorical features. And yeah, even random forests with more hyperparameter optimization tend to do better. All of the neural networks are here at the bottom. The very simple MLP is the worst, followed by a ResNet. The two sort of tabular aimed, more complicated transformer-based models tend to be somewhere in the middle, but generally they are still sort of quite a bit outperformed by just sort of standard tree-based learners. And yeah, that's basically the pattern you see all throughout this paper. And so the question is, why is that? Why do tree-based learners do so much better on both regression and classification tests? It doesn't seem to be just due to numerical features versus to categorical features. There seems to be something about the inductive biases of these methods that just help them work a lot better sort of out of the box than any of the neural network-based methods, even accounting for hyperparameter tuning. So the one of the things they do to try to get at this is they smooth the output. The idea being that, let's see. Um, so yeah, so if you basically smooth the output of all these models, how does it hurt the performance? The idea being that a gradient-based, sorry, a tree-based model might be able to learn sort of less smooth functions, like neural networks might be biased towards smoother functions that might work less well out of sample. And that the tree-based models can make sort of arbitrarily disjoint and like sort of have sort of sharp edges in the functions. Um, and so if you smooth the output of them, how does that hurt the performance? And so they do this with this Gaussian kernel smoother, and this is just basically increasing the amount of smoothing. And this is the normalized test set score. And so you see that smoothing the output of like the gradient boosted tree or the random forest hurts the performance quite a bit. The gradient boosted tree and the random forest have some of the best performance when they're not smooth at all or at zero. But then as you smooth things quite a bit, all the methods have very sort of similar performance. And the drop off for the FT transformer and like the ResNet is much smaller, and they end up at a sort of very similar place after smoothing. So this suggests that it does have to do something with the smoothness of the output. These neural network-based models are giving you sort of smoother outputs that is actually hurting their performance. And these tree-based models are sort of making these much sharper functions that help with generalization performance. And so that's sort of, yeah, I mean, we do know that neural networks sort of prefer smoother things, but it's kind of amazing how much that seems to hurt their actual performance on a lot of these tasks. So that's, yeah, this was this first finding neural networks are biased towards overly smooth functions. Let me see, I think there was a fun plot of that somewhere in here. Yeah, so here as an example what that looks like, this shows the decision boundary of a multi-layer perceptron versus a random forest for two of the most important features on one of the data sets. And so you can see the multi-layer perceptron has this decision boundary that is very sort of smooth and very, where the decision boundary for random forest is much more complicated and has this little islands of things that of things with the decision boundary on each side. So it's sort of able to isolate maybe much more complicated interactions between things, where these neural network-based models are not able to capture this sort of very fine structure into the functional relationship between things. Okay, let us move to any questions so far?
The hey MDO,
Yeah.
the sort of fine structure, you said that it can't be captured. Does that just go away when you have a lot more parameters for the neural network?
Probably not completely. I mean, yeah, it definitely helps to have more parameters. And at sort of the limit where you can sort of over parameterize something and fit the data perfectly, it probably goes away to some degree. But yeah, there's still going to be this bias towards smoother functions, just sort of due to the structure of like rectified linear units and linear combinations of features and whatnot. Any other questions? Okay. The next thing they look at is how unimportant or uninformative features affect the different architectures. And they use basically a random forest to compute a feature importance metric for all the features, and then sort of remove features either randomly or based on this metric. And see, and also basically adding just noise features. And let's see. So yeah, so this is a plot showing that as you as you remove features in decrease the order of random forest important, that your the normalized gradient boosted tree test score basically gets worse and worse as you'd expect, but quite slowly. And this is basically comparing a few different methods. Let's see. And also, so yeah, let's see. So removing features going from 0 to 75% for 4 different methods. Basically, removing features hurts all the methods. It hurts, and let's see, this is, and this is also percentage of uninformed features added. So this is if you add a bunch of sort of noisy features to the data. I think this one is maybe a little bit more informative in that you can see that as you add more and more sort of just garbage features, it hurts the ResNet the most. It hurts, and it hurts the other methods sort of roughly equally proportionally. But yeah, both the gradient boosting tree and random forest are sort of least sensitive to having these noisy features added. But there is, let's see. But yeah, I mean, basically their point is MLP-like architecture are not robust to uninformative features. And one of these reasons is that MLPs especially are just sort of linear combinations of all your features. I mean, all the weights are learned, but you're sort of starting off with random weights, and so you're the first sort of layer is mixing to some degree all of your features, and so that as you add more and more uninformative features in that first layer, it just sort of pollutes what is being learned in each subsequent layer of your multi-layer perceptron. And so having good feature selection is especially important for things like MLPs. It's, yeah, I mean, having uninformative features hurts all architectures. So features important, feature selection is important for everything, but it's especially important for multi-layer perceptrons. But the thing that I think is sort of most relevant and interesting is this idea that the data are not invariant to by rotation. So neither should be the learning procedures. And this sort of goes back to this idea of what MLPs are doing in the first layer. And so how they sort of evaluate this is if you basically put all your features through a rotation matrix, which is basically just sort of, yeah, basically just linearly combining them in all sorts of different ways, maintaining the same information, but your new dimensions are just sort of all your features mixed together in various ways. So you just sort of rotated the space, which is essentially what the first layer of a neural network is doing. But what you find if you do that is, so if you do no rotation versus rotation, so if you just keep the data in sort of natural form and don't apply any rotation matrix first, you see this, you see the pattern where the gradient boosted tree and random forest do quite a bit better than the other methods. But if you apply a rotation matrix and sort of are linearly mixing all the features together before your learning algorithm, you find that actually the neural network architectures do better than the tree-based methods. So the mixing things together actually seems to hurt the performance of gradient boosted trees and random forests. And people have seen this in the tournament to some degree, like when people are doing like PCA on the features and then trying to do learning after that. Especially if you do a tree-based learner after running PCA, it tends to not work very well. And so, yeah, this is a good reason why. And I mean, and the way I see what and what they describe happening is you are sort of mixing features that have very different properties. Maybe you can think of how well a feature, how good of a feature it is, like what is the sharp of an individual feature. And if you're mixing features with all sorts of different properties, how well they relate to the target, their individual signal noise, you're kind of mixing good features in with bad features. And a tree-based learner is able to kind of look at features one at a time. It's literally at every split of a tree, it's evaluating a set of features individually and deciding where to split. And so its ability to consider features one at a time is sort of lost after you do this rotation, like a PCA or something. And so yeah, so it is kind of interesting that these other neural network methods are hurt a little bit by rotation. The ResNet's not actually hurt at all. And that suggests, yeah, I mean, the first layer of ResNet is reducing the rotation itself, and so another rotation isn't hurting anything. The transformer model is hurt a bit by rotation, which suggests that transformers are better at not just mixing things together through their intention mechanisms. They're able to kind of select features, maybe consider them more individually than just sort of having everything mixed together. But there's still there's still a fair bit of mixing within them, and which is why they're not sort of doing as well necessarily as the other methods. So those are kind of the main points of the paper. They do perform a bunch of different experiments and sort of show how across different data sets. They have a lot of plots here at the bottom, sort of just showing different training sets. Here's like a large training set. But you still generally see the XG boost is very, very hard to beat across a variety of different data sets. I would love at this point just to have people ask any questions or share any sort of their experience with these things. I know JRB has actually had quite a bit of luck in actually using neural network architectures in his Numerai work, and I'd be curious to hear what he has to say about this, and if he has any sort of tips for people for using neural network architectures, whether he thinks it's sort of feature selection that is important, or just sort of more architectural things in trying to make neural networks have some of the better inductive biases that tree-based learners have. JRB, are you here? I don't know if you are here. Okay. Does anyone have anything they want to say or any questions they want to ask?
Michael,
Yes.
you were showing how the feature adding bad features hurts models, right?
Yes.
Adding noisy features, it hurts neural networks and it hurts gradient boosted tree models. But gradient boosted tree less so. Do you think that that's also? I mean, I think some people in the Numerai tournament kind of think, well, Numerai's prepared all the features, therefore we can use all of them and should use all of them. But maybe this is saying, well, if you can remove a few of them, that could be very, very helpful. Do you think that's true? Like basically feature selection is a very important thing to do well.
I do think I mean we try not to include like garbage features, but there probably are features that you could would maybe do better without. I mean we sort of are biased towards giving people more of the data and more giving them sort of more options, because we don't want to sort of say that we know for sure a feature is garbage or not if we think there might be some value to it. But I mean I do think feature selection it sort of depends a lot on the model, and so different models seem to do better with maybe different features, and which is why we wanted to include more features. So I think feature selection is something people should take very very seriously. I mean, and also it just like it will greatly reduce the size of the data you have to work with, because we have quite a lot of features, and it can be a bit cumbersome to work with sometimes. And it will also make your models more unique. If your model's using a different subset of features than other people, it's more likely to like have true contribution or something. But yeah, I mean, it seems like if there are features that are actually just garbage features in there, which seems totally possible, you would be helped by doing some feature selection, just because having garbage features will degrade your performance a little bit.
What is your best way to do feature selection? What do you think is the sort of state of the art way to do feature selection on Numerai?
Yeah, so I had a forum post using Baruda Shap, which I think is a pretty good feature selection method. It is quite slow, and I posted a set of features that it came up with. I think that's what is in our like small feature set. And I mean, no feature select and a selection method is perfect. One thing with like Baruda Shap is it is sort of dependent on what model you use for doing the feature selection, because it is basically adding it's it's basically like one of the things that's doing is like adding fake features and looking at how your like Shapley values on the fake features compared to your real features, because you would basically think that fake features shouldn't have any feature importance, and so it gives you a sort of nice baseline for, is this a real feature? If it has a feature importance that about is the same as a fake feature or worse than a fake feature, it's definitely not really helping. And that's a sort of Baruda idea, and the Shap part is just using the Shapley values as the feature importance metric. I think that's a pretty powerful method, but you do have to kind of be careful with it, because it is sort of giving you a set of features that work for the model you're using at each iteration, and it doesn't. Those set of features won't necessarily work as well if you change the model after that. So that's an important caveat for that. Yeah, I mean, there's a lot of sort of feature selection methods that like Marcos talks about in his book, like mean decrease accuracy and sort of feature permutation ideas, sort of looking at if you remove or like permute a feature, how much does it hurt your out of sample performance. I think those are all great methods as well.
As you said earlier, the like era is a kind of a fundamental unit on Numerai.
Right.
And none of those methods use the eras, I guess. But I guess
but
something like
to, yeah.
Yeah, because there was that presentation in a New York meetup, Numerai meetup, where it was shown how I can't remember who did it, but it was shown how you can compute the Sharp of each feature, and use that as a method to select good features.
Yeah, I think that's a great way to sort of just select the if you're just doing if you're just looking at the features and they're sharp with respect to the target, that's a sort of good first pass. That, I mean, doing something like that kind of misses potential interactions that might have like higher sharp. I mean, there might be a feature that by itself doesn't have a good sharp, but when you condition on it, gives you something that actually does have a very high sharp. If you basically some other feature given this feature's value, so this sort of interaction might actually have a much higher sharp value, and you would miss that kind of thing just looking at them one by one. And that's where things like the Shapley values are much better at kind of teasing what are the important features out, because they sort of are in terms of a nonlinear model. But yeah, I think trying to do all your evaluations error-wise is important, and you can adapt all these methods to, so you could compute like the Baruda Shap like per era or something, or compute whatever metric you're deciding for per era, and then average, or find like it's and then it's also a question of like, how do you select if you are computing the statistic per era, do you do something like the Sharp, like the mean over standard deviation, or do you want to find like the best, like worst case scenario? So like find the thing that has, because like basically you'll see a lot of variance era to era, and so do you want to sort of like minimize the worst case scenario? That's another sort of way you could do, rather than just selecting the one that has a like based on the average, or like Sharp, like look at the minimum. Wigglemuse.
Yeah, so I guess the big question. Well, everything is you say is correct, of course. And I've noticed all this, for years, trying to get good core, and MMC also in the old days, and it has to do with the inductive biases and not, sort of using those statistical mixing methods like PCA, at least to replace the data. I think it can work if you augment the data with it, to make more features. Although I used to say that, and then someone would come along and say, this model uses PCA, it's, it's rank number 4 or something. So I'm often just, not doing the right, correct thing. But in this age of TC, the question is, what is good performance? Because it seems like this, it's doing better with trees and so on, is that sort of measurable validation, the things we can validate with core. But with TC, it's just all over the place. I mentioned this last time. I mean, I've got a model that was made with B3 data, made to get, core and MMC, and it's humming along. It gets core. It hardly ever is got a negative core, and it sucks at TC. Once in a while, it crosses 0 and then goes back down, but it's just no good at TC. And we look at the leaderboard, and we see most of the highest models on TC do have pretty decent positive core, but they are not the highest core by any means. And we also see, if you go looking, we see plenty of, decent TC models that are not getting any core at all. And I mentioned, so I mentioned this last time, is when I started getting good TC on some models, when I started messing with the data set and doing that sort of statistical mixing, and basically my whole approach now is just like a shotgun, where I am, it's not random, but I'm picking out every inductive bias I can think of and trying to make a different model with a different inductive bias and based on these things, and then just see how it shakes out. So like you said, everything here is correct, but I wouldn't necessarily take that as discouragement to do these other things, because that's where the gold is possibly still. So
yeah, I mean, I think and I think a sort of good, what you're doing is sort of the right thing, and just starting to think about what are the inductive biases of your learners, and trying to see what inductive biases seem to work for this particular problem.
I always thought that way, but nothing ever worked other than sort of a straightforward thing. And all these models I'm making now, they're generally terrible at core, from what I can tell.
One other inductive bias they didn't mention here that has always seemed important to me, between tree-based learners and things like neural networks, is the extrapolation inductive bias. So tree-based learners extrapolate sort of in a like piecewise constant way. Like if you just think of the most simple tree where you cut your space in half, it basically assigns one value to one side and one value to the other side.
Right. Anything over that border is just the same as the border, right? So exactly.
So everything in that half space gets the same value. So it's sort of this piecewise constant. Whereas like an MLP or neural networks will generally have a sort of linear, or like a piecewise linear inductive bias. So your extrapolations kind of continue in a sort of linear way outside of the data. And so you can see, like in this this plot, there's this this decision boundary sort of is slowly changing over this, which is sort of just indicating it's due to partially to the inductive bias of the MLP, where it's basically just this piecewise constant function over the space. And this is hard to think of in high dimensions, and all this stuff is actually happening in high dimensional space. You can sort of visualize it in two-dimensional ways, but what generally happens in our like very high dimensional space, we're usually in a part of the space where we've never been in before. Like a new set of features is pretty far from any set of features that we've ever been in before. And so how your model generalizes to this new point in this high dimensional space seems to me pretty important. And whether or not a sort of piecewise constant inductive bias and how you extrapolate to this other place is better versus like sort of piecewise linear it's sort of, and it might be different for different features. Like maybe a piecewise constant for some features is a better inductive bias for extrapolation, where a piecewise linear might be better for other features. And so like the meta model or is sort of mixing all of these together and hopefully getting sort of the like a better inductive bias overall. But yeah, I just wanted to highlight that other inductive bias difference between these types of learners.
That brings up a general question I've wondered about the data for a long time. If we get the data, of course, not in raw values of any kind, but buckets, and the buckets are always the same. So you would think that at least with some features, the raw values are, you know, not necessarily equivalent. In other words, from era 10 and era 1000, some feature, it's like it's recentered and rescaled. So is it real, you know, does that make sense? Like the 0.5 value for era 1000 at a feature could be quite different, or is everything, are all features sort of inherently relative anyways?
It's more like the latter. Yeah, I mean, we're turning everything into basically just everything being relative, because because we care about in the end is sort of the relative ranking of stocks, rather than like their absolute performance. So we turn all the returns are in sort of relative terms, and all of the features are in sort of relative terms.
And that's something I've done myself when, you know, like if you have a model where you need to scale the data just to get it into the model, you know, you z-score it, say, you're supposed to save the mean and the standard deviation of the data that you use to put in the model to transform your new data, right, to get it in that same space. And I do that sometimes, but other times I'm just like, I'm just going to scale it on its own terms and then call that equivalent. And sometimes it works better. So I've actually done quite a lot of that. And sometimes it's, you know, it's quite extreme where I'm, you know, like if you do a PCA, you know, you're supposed to make the data like the original data, but sometimes I just scale it on its own terms and then apply the whatever. And it works quite well and quite different than if you did it the other way. It's like a whole new inductive bias that way. And then again, with TC, we really need to be able to validate our TC. So I hope that sort of thing is coming. When I'm making a core model, especially with all the data we have now, I mean, you can tell more or less if it's decent, but you can make a very good core model and it's just size to TC. You can make it, and then you just put something forward and you just got to wait. I hope we can get some tools along those lines.
I wanted to ask, I know people, I mean, people now have access to like past meta model scores, and I wanted to ask if people have had luck in using them and trying to pursue TC based models and been able to make sort of more sense out of TC now that they have access to like past meta model scores.
I just started looking at those in the last week. I was actually going to use them, and I think a lot of people are, as target or residuals to a target, or, you know, as some form of target adjustment or something, just because it's a new thing.
Yeah, this relates to.
Even if I had made a model, I mean, we've had them for what, a month or something. Even if I had made a model, I would have no idea still, because the TC can be so random that you just don't know until you've got like 20 errors or something.
Yeah, I mean, so this relates to some question somebody had on Slido about if we could give sort of the optimal TC predictions, or yeah, sort of like what an optimal prediction for TC would
Yeah,
look like.
yeah. What would be a perfect
Um,
TC or something
I
like that?
I mean, it's a bit hard to answer, but I think a good sort of proxy would basically just be something like you said, residualize the targets to the meta model scores. Basically, just do like yeah, just do like a neutralization or like Gram-Schmidt orthogonalization of the. You're just subtracting off from the target the part of the meta model prediction that is correlated with the target. It's a very small part. I mean, the correlations are like 3% or something. So you're only like, so you're not changing the target that much by subtracting off how the part that is similar to the meta model. But after doing that, that if you sort of if you train towards this new residualized target, that would sort of be like if you were able to get that perfect, that would sort of give you perfect TC, or sort of like the highest possible TC, because that, I mean, that target is created like from returns and will have returns that are orthogonal to where the meta model is pointing you, and so that would give you extremely high TC. Obviously, it's going to be hard to do because there's the meta model has a lot of the information that is sort of learnable from things, but this residualizing to the meta model scores seems like a great way to try to get at TC.
Yeah. Well, I mean, is there a solid suggestion there? And let's say I build a model today. What can I do to see if it's going to get TC, save submitting it and waiting? If I look at those meta model scores and look at the residuals, and then the core left over is good, would I then expect to get TC? It's hard to even tell because TC doesn't even have a target, right? We have these targets, but it's not like it's the residual of the nomi, as people sort of complain about, right? So they're like, hey, I got a good core, and then where's my TC?
No, I mean, it is for sure tricky. I mean, if you look at the top of the leaderboard, which is sorted in terms of TC, you can see that there are sort of different strategies that work. I mean, you see some people that have that are near the top of TC have extremely high correlations to like Jerome 60-day target, which is one of the reasons we put that on there. But you see like some of the people who are doing very well on that target are doing very well in TC. You see, one thing you generally see is a lot of the people who have high TC, their correlation of the meta model is like 50% or under. I mean, to have like the absolute highest TC, you clearly need to have very low correlation of the meta model, but you also need to be giving a signal that is consistently good over time. So you need to have sort of consistently positive core, consistently, while being uncorrelated to the meta model. And yeah, there's going to be variance week to week, just depending on the markets, and it's a bit more volatile metric, and so you do need to give it some time. But you see that people who consistently have positive core while being very uncorrelated with the meta model are often doing quite well. And it's kind of hard to say like how to get TC because clearly there's multiple strategies that will work.
Right. Do you think that if you are not getting good core, even negative core, that you're just not going to get TC, or whatever TC you are getting is spurious and random? Or is the sort of good core correlated with good TC just a subset of the good TC space? I mean, the models I've been making run from 0 correlation with the meta model to about 24% with the meta model, and those are more normal. A lot of them are just 0. They get negative core. Sometimes they get, I mean, the core just seems random. And then I'm just sort of hoping that the TC is good. I mean, I don't expect it to be, super consistent, but if it's good 60% of the time, it's profitable. So is anything like that probably just nonsense, or you think there's something that could be in those spaces?
I I would expect that if your core is like on average 0, it's likely to be just noise.
I mean, I'm positive some of them are, but some of them are very interesting, and they go, you know.
I mean, it's also worth looking in the tails too. I mean, if you are getting sort of positive correlation in the tails, and it's worth looking at. If maybe you get 0 correlation overall, but if you get positive correlation in tails consistently, then you would expect to have good TC as well.
Right. Then I have to test that myself later.
Yeah. So yeah, I mean, the tail effects are especially apparent in TC. Our current correlation scoring is sort of too insensitive to the tails, and we're actually planning to move to a newer version of correlation that basically a Pearson correlation on like Gaussianized, rather than like, because our current correlation scoring, we rank normalize your thing, and then do correlation, Pearson correlation with the target. We plan to sort of move to just like a Gauss rank version, so we're just Gaussianize things, which will emphasize the tails in the correlation score as well.
Well, I mean, nomi moving from a flat target to nomi Gaussian did that to some extent, right? So now you're talking about doing that to our side as well. So.
Yeah, exactly. Doing that also has a nice advantage of the correlation metric can actually go basically up to 1, because right now the sort of mismatch in the distribution sort of caps the correlation score at like 0.92 or something.
0.91. Yes, I brought this up a long time ago.
Yeah.
You said, he'll never get there anyways. It doesn't matter.
No, exactly. It practically makes no difference at the levels of correlation we're at, but it is a nice property to have the metric actually be able to go between 0 and 1. And the new metric we're going to be moving to at some point, we'll do that. Yeah, I mean, this will probably also come with some new targets as well. We'll probably move to a different scoring target at the same time, but there'll be plenty of warning for all of that. That's still
switching topics. You were talking about feature selection, and you know, how you probably need to drop some, or maybe some are garbage or whatever. I was just looking at something a couple of days ago that was, I think, was using genetic algorithms to find subsets of features that work together. So rather than, you know, picking some one at a time, where I think you're going to end up with the same thing, because there's a lot of redundancy in the data. So there might be this set of features that go together in a sort of a similar but overlapping but different set of features, and you kind of need to drive yourself to one of the other subsets. And if you always start at the top or the bottom and add one at a time, you're going to tend to get the same ones probably. But there are some other ways to do it. But I think almost all of the really good methods for feature selection are inherently, like you were saying, tied into the model you're using, because it just matters so much what the inductive bias of that model is. So I think everyone has to sort of find that solution for themselves, where they sort of pick the model they're going to go with or try out, and then look for those subsets.
Yeah, exactly. But yeah, there are a lot of like good packages and ways of doing these now. But as I said before, I think using error-wise statistics is probably very helpful for doing feature selection, because it is our problem is a bit different than most data science problems, in that we want to be good sort of at every era rather than every sample.
Yeah, and I think a problem with a lot of the methods, and possibly with this whole paper actually, is that it's better, but it tends to become kind of linear. And we've got this thing where we sort of want to avoid linear just because it's linear, you know. So that's sort of a Numerai wrinkle to these sort of, this is better than that. But what happens when you force it to be a non-linear response, you know, to the features?
I mean, well, yeah, I'm not sure what you mean by it becomes more linear. I mean, so like a
Well, I
random
mean, you get more feature exposure that you're
Okay.
going to neutralize out.
I mean, yeah, I think like MLPs and neural network based things, I think will generally take on higher feature exposure since they give sort of more linear answers overall. I mean, there's been papers for a long time just sort of showing that neural networks are often way more linear than people think they are, or they have really large linear regimes where they're well approximated by a linear model in various parts of the regime. Like in this plot I'm showing here, you could see that it would be much harder to approximate this random forest decision boundary with a linear function, where you can imagine a linear function would actually approximate this MLP decision boundary pretty well.
But with that mixing, you get a de-emphasis on individual features, and random forests or any kind of tree can tend to fixate on very specific features that you need to dial it back on at times.
But in a particular way, I mean, your feature importance isn't the same as like linear dependency. Yeah, you could potentially have a feature that has very high feature importance, but actually isn't that correlated to the output of your model.
Do you think that's still a problem? Maybe just a high dependence. If this feature, even if it's nonlinear, is just not behaving this week, then there goes your model.
Yeah, I mean, it's
Robust
definitely
in terms of robustness.
Yeah, there's definitely. I mean, if a lot of your, I mean, because it's sort of saying like how dependent are all of your splits and whatnot, are sort of how is the sort of output of your model dependent on what the current feature value. Yeah, if that feature starts behaving very differently, you can still kind of mess up your model. And yeah, the sort of the way we do like feature neutralization is kind of a linear hack, and in some way you'd maybe want to sort of balance feature importance, this sort of nonlinear dependence on things, and make that more balanced across your features. The hyperparameter we use to help that is like the call sample by tree, where you're basically for every tree you're only looking at a subset of the features. And so when you do that, each tree is only looking at a subset of the features, and so you tend to, over the set of trees, use each feature a bit more and sort of tone down how much you're using any one feature, rather than if every tree could look at all the features, it's always going to pick the best feature, and you're going to get a lot of feature importance to like the best features and take a lot of feature risk that way. So this sort of that hyperparameter helps with it, but there isn't explicitly a way in these boosting algorithms to sort of balance feature importance. And it seems that would be a cool thing for someone to work on, is to try to modify the split selection thing, where it can sort of try to balance feature importance to basically like have flat feature importance or something. But that would, yeah, you'd probably have to get into the guts of a tree learning algorithm, where you basically have sort of a running total of your feature importances, and you sort of bias your splits to use features that have like currently low feature importance to try to balance it or something.
Right. All right, that's all I have.
Cool. Yeah, thanks for the questions and comments. Anyone else have anything that they want to talk about before we wrap? Because we're coming up on the hour. No? Okay, guys. Well, thanks so much for everyone who showed up. Please give us some feedback in Rocket Chat or via email or whatever. Please, yeah, let us know what you'd like to talk about in the future, and post any questions to Slido. It's a lot of fun talking to you guys and talking about this paper. I'm curious to see what if this changes your thinking on anything, and if you have any further questions, yeah, but just post them in Rocket Chat, and I'll try to respond to all of them. So thanks a lot, and see you guys next time.